Hey gang, we're back for another Toolbox talk. It's kind of a catch up and a quickie. Today I'm going to discuss a few things we've been doing besides hunting flies. And the main talk will be just a quick moments on mechanical advantage and particular reverse mechanical advantage and how it affects your strength of your anchors, your anchor points, what your pulleys are hung on, etc. Because it changes things a lot. Just first notes, we haven't posted in a while. We've been very busy doing other things. We waited forever for our new load cell to come in, our new beam load cell that's computerized with its little box so that there's no more digital equipment in this device, because breaking stuff at 10 tons, the shockwave, it doesn't bounce around because it's suspended and it's buffered. It can't hit anything. But the shock wave that goes through the digital stuff blows out the normal dynos. So I ate up two very expensive dynos, a couple grand a piece, doing a bunch of tests. And I got partway into the Sutra harness pick pulls, and it was just not reading correctly. I couldn't read it. And I know I'm blind and old, but when the digital board doesn't show anything, you can't read a number that doesn't exist. So we were forced to join the techno age. We've got this load beam cell, which is removed and remote from the motherboard, which you drop. Here it is, and then that plugs into the computer. The difference is this will read about 1,000 times a second. It'll graph. I'll be able to just get a shit throwaway notebook computer to run it all on. So we're gonna be building and installing that, certified, so we know we're right. Because when the digital starts acting up, it's hard to verify. That's why I started using a couple of dynos to cross-check stuff. Anyway, so that's one project we're back into. The second project is we're dealing with our press. We're building, we have a hydraulic press, but now we're going air over oil on hydraulic. So this morning I'm filthy. I've been reinforcing and making the 12-ton press operate with a foot pedal. And that way I can bend anchors, floor anchors and things out of heavy 6mm stainless, kind of like the Petzls, only thicker, bigger, heavier. And I can make my own fixtures for plate bending, and it's strong enough. And I hate doing the Jackie bullshit, so we've got an air over 12-ton hydraulic jack, so I just push the pedal and it does the deal. So that way I could actually work on bending stuff as opposed to just messing around. So we reinforced everything to hold the tooling that I'm building. So it's just been one of those mornings. But we had an issue lately with some of the people in mechanical advantage, and in particular reverse mechanical advantage. Now, mechanical advantage, everyone knows. You run a 2-to-1, the weight's half as much. You run a 3-to-1, the weight's a third as much. You run a 4-to-1, so it's a quarter. Now, this is in a perfect world. Forget the friction on the pulleys and forget forget all of the other incidental crap. Technically, that's how it works, okay? That's the theories. Now, your pulleys are going to have a percentage of friction, so it's not going to actually be that exact number of math, okay? So you have to think about these things. But even when you do that, the rope you're pulling, you'll be pulling twice as much, 3 times as much, 4 times as much rope on the pulling end, meaning whatever machine, winch, hand pull, whatever, will be pulling that much percent less weight, but it will be pulling that much longer to achieve the same distance, because you'll have to pull 2, 3, 4 times as much rope to get the same movement of the object, okay? So that's the normal mechanical advantage, all right? That's the standard. If you're gonna lift something heavy, you put a pulley on it, dead it to the roof, come through another pulley and pull on it, and it reduces the weight by 50%. I'm not going to get into diagramming all this out because I could spend hours doing it, and Jay Glaram's book on rigging shows it. There's a whole lot of mechanical advantage rigging online to look at, so if you really need a visual interpretation of this, go find it, because it's not hard. The issue I really want to get into is reverse mechanical advantage, meaning 1 to 2, 1 to 3, which means that you pull half as much rope, but the weight is twice as much. Now, this sounds counterintuitive, because why would you do that? Well, it particularly comes in when you have machines that are doing the pulling, i.e., for example, a ratchet. Okay? Now, a pneumatic cylinder, I can put in X amount of air, and depending on the face area of the piston, I can exert that much more force. Pi r squared will be the force times pressure. Okay, so that means if you're doing it in imperial in a 4-inch ram, for every PSI you put in, you get 7 pounds of force. Okay, so you can do the math since it's 15 PSI to a bar. So 15 times 7 is going to be 105. So you're getting 105 pounds of force per bar, or 50 some odd kilos per bar. So just do the math, guys, but you see how it can multiply the force. So now, especially with ratchets, we run them in reverse because it works quicker per unit time. So if a ram contracts at a specific rate under force, pulling X amount of weight, okay, if you 1 to 2 it, reverse it so that now it's pulling in a bite, you're pulling twice as much rope for that unit time that the ram is moving. So for every meter the ram moves, you pull 2 meters of rope in the same time frame. So it's much quicker, okay? Now, it also gets to be if you've got a 1.25 meter, a 4-foot ram, and you need to pull twice that length, 1 to 2, now you can pull what you need with the stroke of your ram. And sometimes you'll use a 4-foot and or 125 ram for a 10-foot pull, okay, or a little over a 3-meter pull. Okay, so how do you do that? You reverse it. So now you pull as much rope as you need. You will need to increase the force to make up for the weight increase, because now you've increased what's on the end of your line by however many parts of line you have moving. And in reverse, it's really kind of tricky. On the rams I have, the way it's set up, you have to count the moving lines to know if it's 2 to 1, 3 to 1, 4 to 1, because if you redirect, that's not a working part of line. So if you come from your object through your head block and then through your ram and back out to a redirect to a clutch, that's only 1 to 2. If you come down and you go around again and dead it, then it's a 3. If you go again around the pulley, so now you have a 4 to 1 in reverse, and dead it off, you have 4 moving parts of line. The last tail, which would be a 5th line, goes up through a redirect and back to your clutch, or ties off at your clutch, however your system is set up. But an easy way is to calculate the moving parts of line. Like when that pulley moves, how many lines are moving? And you'll know if it's 1 to 2, 1 to 3, 1 to 4, and the same works for a 4 to 1, 3 to 1 in the other direction. You just count moving lines. You count parts of moving lines. Now, unlike positive mechanical advantage, reverse mechanical advantage, or when you say 1 to 2, you end up having double the weight of your object on the line, okay? But the 2 parts of the line that are pulling are going to be half the load. The anchors at both sides are going to be seeing the force you're putting in and the weight. So if you've got 100 kilo force you're pulling with and 100 kilo of weight out there, your anchor points that these are going through are going to see double that. Just like if you hang a pulley in the ceiling, put 100 kilo on the floor and pull with 100 kilo of force here. You're pulling this line at 100, this weight is 100. So now what does that anchor point there see? 200. Now, no big deal, right? You figure this out. But when you have motor, engine, power, i.e. a ram or hydraulic or whatever, and now you can go reverse 3 to 1, say it correctly, 1 to 3. So that means you're pulling 3 times as much line per unit time, okay? Each part of the line in the pulley system as it's moving apart from one another is seeing 1/3 of the weight. So your performer is not seeing all of that force you're putting in. It's just seeing one part of the line. But your compounding pulleys, which may be anchored to 2 points, whatever they are going to be seeing 3 times the load that you're putting in, meaning what's being put in from the ram and the weight. So it's going to be 3 times that. So if you start going with 10 bar, 150 PSI, you're seeing 1,000 pounds of force put on the anchor on one side, okay? Which is far different than the 100 kilo of the performer at the other end. So your pulleys in your anchor points are going to see a huge amount of load. And this is something you really need to consider, whether you're doing it between 2 fixed points on a stage, whether it's like I set up between on the truss, but you have to acknowledge that you're pulling with all of that weight at these 2 pulley points. Between the 2 points, from the engine input to the engine output, you're tripling the force or doubling the force or quadrupling the force on these points. Now, it doesn't matter because you have enough power, you just add either more pressure, you add more force, you add more whatever your engine operates off of, okay? And you get the result you need, but you're putting huge amounts of force into these anchor point systems, okay? And your compounding pulleys need to be anchored to something. They're not just hanging in space. It's not magic, okay? And remember that when you're running your systems, because we've had some people set up systems and then also not acknowledge that you're adding these huge amounts of force into the system and your anchor pulleys are seeing all of it. Plus, if anything goes weightless because of the speed of movement and then slams back into it, you have a factor 1, 2, or 3 quote unquote fall. So you're multiplying those forces. So in theory, if you're putting 1,000 kilos of force, let's say, into the system, your anchors are seeing double that. And now if you're going into free fall and then dropping another 100 kilo object, another few meters, a factor 2 fall worth, okay? So you know you can work all this out with negative acceleration formulas. You can calculate all these forces. So this is a mental exercise. I'm just saying, you got to think about the forces on these anchor points, because everybody just dials stuff up and, I'm going to go 1 to 3, 1 to 4. Well, maybe that's not the best option. There may be other options to use in your system so your devices, i.e. the way you set your ratchet up or set your anchors up, aren't going to see so much of that load. You try to distribute it elsewhere in the system, okay? This is really important. I say the easy way to think of it is just always go back to the 100 kilo on the ground through a pulley and pulling on a rope. If you look at the mathematical formulas in all the books, Glaram's book goes through this a lot. It's a really, really good rigging book. It gets a bit much for a lot of people, and it is done in imperial, so for some of you metric folks, it's going to be difficult. But basically your anchor point, because you're pulling here and pulling here, equal forces, you've doubled your force, okay? That point above is seeing twice from that part of the line and this part of the line. So if you think about your pulling, think of that as your system, and you're pulling that pulley. If you were moving that pulley to create this motion, you're going to be pulling this weight and this weight. So that's 200 kilos. So your anchor is seeing that. Now, if at any point you do it really fast and this thing goes airborne, now it has no more resistance, and you get to the end of your movement and it falls back into that rope, now you're compounding that 200 kilos with the force of this falling into free fall and stopping dead. So now you've you've accented that by X amount more kilos, okay? And we already know that on a hard fall, you can generate 3, 4, 5, 6, 8 times the body weight, depending on what you're doing and how dynamic the fall is, okay? We already know that. It's been published in all of the acrobatics stuff. There's a really good French chart on all of the various dynamic movements and how much more body weight they generate. Straps act as like 8 times the person's body weight. So you'll never have a 100 kilo strap guy, but call it a 100 kilo dude, he's going to generate 800 kilos of dynamic force. Okay, think of adding that into a reverse mechanical advantage system. It's going to send your working hardware through the roof. Remember, most of our stuff is repurposed and we try to keep it fairly small and workable, hand workable. So we use a lot of climbing stuff. A rock pulley is only good for 2.2 tons, 22 kilonewton. It's a rough conversion. It's 200 and blah, blah, blah pounds per kilonewtons. I mean, you can just, it's roughly 2.2 tons, okay? Well, that's great. That's an MBS, okay? So it doesn't take a lot to add up to that in just working, let alone design factor. So you eat up any of your safety margins, you eat up any of your design factor, and then suddenly you have a catastrophic event, which is why I'm mentioning this, because you start bending anchors, you start bending plates, you start bending hardware, you start blowing out, if you're using carabiners instead of shackles, because they're rated MBS. Average carabiner is 22 kilonewton, 2.2 ton. That's a normal, errata work access carabiner. They're not, you get more. You can get, I've got 5-ton carabiners, MBS. But that's an MBS, it's not a working. So what's your design factor? If I've got a 5-ton carabiner and I want to say it's a 5-to-1 safety or design, I hate the word safety, but a design factor, it means I can work safely at 1 ton on it with breathing room. Well, 1 ton is half of what your pulley's MBS. So what's your pulley's MBS design factor? You're going to go 5-to-1 on that, so you're going to be 500 kilos. Well, if you're operating on this and you're pulling with a machine on an inverted 1-to-2, 1-to-3, 1-to-4 type situation, your forces mathematically go up enormously, and you are instantly, completely out of the zone of not only working, but you are over the limits of all the MBSs on your equipment very, very quickly. So you need to think about this, especially when you get into trying to move things quickly with force. And that implies you're going to be using a mechanical advantage in reverse, okay? Because moving things quickly requires a lot of rope to move, and you aren't going to do it if you're in the traditional mechanical advantage, because you have to move twice as much rope for every iteration. So at 2-to-1, it's twice as much rope. 3-to-1, it's 3 times it. 4-to-1, but in reverse, it's not. It's the other way around. So if you move 1 meter at a 1-to-4, you've pulled 4 meters of rope. It's going to happen way quicker, a lot quicker. Okay, and now you've moved in that same time of stroke, you've moved 4 meters instead of 1 meter or 2 meters or whatever your compound is, okay? So it accelerates your numbers of loading. And like I said, I always go back. The easiest way to think of it is a single pulley point. If you do a 4-to-1 and locked it all off and had to pull everything with that pulley above, which is seeing 4 times the load now, you're going to be in a world of hurt. Just how heavy all your equipment gets, how heavy everything has to work, how close to your border lines. And I'm not being super finicky with the vocabulary here, because I could get out the physics book and get really into it, and I don't feel like it. It's just, this is something you need to calculate and pay attention to, okay? And it's not intuitive. It's not intuitive, especially when you're working reverse, okay? So you need to think about that anytime you're using a reverse system. And I've mentioned it before, when you put service loops in your rope. You come from whatever you're doing up through a pulley into a service loop. You take that bite with a pulley and anchor it. Now, the reason you would do this would be to be able to have halfway to the ceiling and halfway to the floor adjustments. So you could take your final point without touching any other marks and move your performer, if the perms are 12 meters tall, 6 meters forward or 6 meters back by just taking up your loop. But your loop, your bite that is anchored, is seeing twice the load of whatever you're putting on that. Okay, this bite rope, your service loop is going to see twice the load. Not bad if you're just, 100 kilo on that end, pulling by hand or pulling lightly, but it's going to accelerate very quickly to where you're going to exceed your clutch's 1400 kilo limit, and it's going to start slipping. So a lot of times if we're working with heavy things like that, I will take this service bite, which is a 1 to 2, and I will anchor at the bottom, come through it and back down with another pulley and turn it back into a 1 to 1 on the service loop, because now I've been able to change this portion of the system back to a tolerable number and design factor. So you need to look at these changes throughout your system. You need to calculate this math, because guys will be set up a ratchet with a service loop. Oh, that's cool. I can adjust everything. Great. They all of a sudden they're up to some ridiculous pressure. They're hitting the button and they're wondering why the rope just goes zzz, right out through the clutch, and they're tying knots behind the clutch to be able to keep it from slipping. And that's not even helping, because now the knot's getting sucked so tight into the clutch, you have just a clusterfuck. You need to think about these forces and how they multiply, especially when using engines, power engines, rams, hydraulics, winches, things that can increase and pull beyond the forces that you would normally be able to pull. Because I'll tell you what, unless somebody weighs next to nothing, I'm not going to put a reverse on them and try to hand pull them up, because they're going to be double the weight. It's not worthwhile. Okay? So just please pay attention, or you'll start bending, breaking, hurting things and people. Okay? That's just today's point, is look, really study mechanical advantage, and then start thinking about what it means when you reverse it, especially for your anchor points, all of your hardware, all of your dead ties, your clutches, all of these things, because your pulleys and your clutches are going to see huge amounts of force. If and when you can mitigate them, i.e. in a service loop, it doesn't take any more difficulty to bring it halfway down, put a pulley on the pulley, back it to it, and tie it off and bring it down and now put it in the clutch. You know, because now you've taken it back to 1 to 1. So whatever force you're putting into the system here, which is now doubled in this bite, you've now reversed it with a mechanical advantage of a 2 to 1 and brought it back down. So you've negated the 2 to 1 in anchoring back to a 1 to 1. Okay? Now that doesn't take away any of the other forces of your other pulleys downline. Okay? But you've mitigated your anchor problem. Okay? And you have to look at each section of your system like this and do the math. You know, just at least be able to be familiar with it enough to look at it and ballpark it enough to be within your safety parameters, within your design factors. This is kind of an extenuation of my other discussion of the simple system and what people, you know, the constant, oh man, we're 10 to 1. Yeah, you're 10 to 1 in your dreams. You know, it's a random bullshit number. And instead of knowing, because no one works at 10 to 1, I can tell you that right now, or else we'd all be using these gargantuan, you know, 3/4 pin shackles and stuff like that. You know, look at the ANSI book, look at design factors, look at, you know, operating, you know, 3 times, 4 times, 5 times for various design factors over events, whether it's a catastrophic, meaning an e-stop situation where it's a sudden, immediate stop, how much force that puts on the system, or on a simple gold tail. What happens if you get an asshole in the rope and it just comes in and sucks in and dead stops on a 20-foot drop with someone? What kind of force is that going to generate? What does that do to your anchors, your upward anchors? Okay, look at those things, because those are the real world numbers. They're not the, oh, this is going this. Look for your worst possible scenario and design your factors from there, okay? And like I said, on ratchets, it gets particularly brutal because you've got, like with my systems, I can go up to 64 bar. Have I ever bothered? No. Can I? Yes. Well, where do I get with people? Well, I mean, they average 10 bar max for people, usually. Now, if I start going 1 to 4, I may be at 20 bar. The performer's not seeing that increase, but the anchors are. Is it moving quicker? Yes. Has it achieved the longer distance? Yes. Have I put more force on the performer than previous? Not really, if you work out the math. because they're seeing one line of a 4-part system. But the anchors are seeing all 4 lines of a 4-part system. And that means that the force you're generating on the engine, the ram, to pull that object is really a lot of force, okay? So you need to look at this. You need to look at how you've set your system up, okay? There are ways to mitigate it, especially for anchors, as I've said. So that's just today's wrap. We're into our projects. We'll be back up and running on testing Sutra harnesses once I install the new cool device. Have to do some machining to change the mounting system since it uses these large rod ends instead of a 40 mil pin like the other dynos. But that's easily done here. I'll get on the lathe and whack some stuff up and we'll go from there. So I'll be coming to you probably with another one in the next week so that you can get an idea of how the system works. And I'm going to do a quickie on how our tester works with the new system and show some testing. All right? So just remember, when using Mechanical Advantage, check your numbers, especially when using reverse Mechanical Advantage. There's a reason we use it. It's for speed, reaction speed, pulling volume of rope over unit time. It works fabulously, but it does significantly increase the forces on every one of those anchor points within your system. Okay? So just beware. And yeah, we'll get you next time around. Take care.